In this video, I'll talk about the types of variables used in research. This is a major research design consideration. It's really important when thinking about your study. What variables do you want to include in your design? I also just wanted to back up and talk about some of the different types of statistics. I'll talk about each of these in more detail in the next part of this course, not in this video. But descriptive statistics are ways that we describe and summarize important characteristics of data. This may include the use of graphs and tables to present those characteristics of data. Inferential statistics are methods that we use to test a hypothesis. Typically, you collect some sample data, you process it, and you use that to make some inferences and draw conclusions about a larger population of people. Some examples of inferential methods include chi-square tests, correlation analysis, t-tests, and ANOVA, which stands for analysis of variance. Variables are any characteristic that is observable and can be assigned different values. This is critical for doing statistics. If we don't have some characteristic that has different values, in other words, that varies, then there's no point in doing statistics. So a variable is not a variable if it doesn't vary. That would be a constant. There's a number of reasons why you might include constants in your research design. For example, you might decide that you want to only work with female athletes, so gender in that case would be a constant in your study. Or you might only recruit people of a certain age, so therefore age would be a constant in your study. But that's not something that you would then go and analyze with statistics. So if all the values are the same, there's no variation. Variation is crucial to doing statistics. We need variables. So just as a quick research example, I as a professor of this course might ask this question: do students who finish the exam faster tend to get a higher score on the exam? So the variables implied by this research question are the time that it takes to finish the exam and the score on the exam. So I could basically collect data on this and analyze them and look to see if there's a correlation. So I'd be doing a correlational study with this. So some characteristics of variables. They're mutually exclusive, meaning that every observation person in your study must be placed into one and only one score or category. So if you have participants, typically, if you're doing an experiment, if you have a control group, someone who's in the control group does not also participate in the experimental group. They're in one and only one category. So let's say these are my data on the number of minutes that it took my students to complete the exam. So what we see here is we do have some variation, which is good. This is a variable. This is mutually exclusive because each person has one number of minutes assigned to them. It's also exhaustive because every participant's score can fall into a category. So I have enough different categories to represent all the possible times that it took to finish the exam, whether that was less than 41 minutes, 41 to 45 minutes, 46 to 50 minutes, or more than 50 minutes. There's no gaps, there's no overlap, so they're mutually exclusive, and there's no gaps, so that they're exhaustive. Variables are also operationally defined. There's some definition that specifies how you are measuring your variables. So some examples: for weight, I might operationally define it as the distance a spring stretches when you hang something from it. I might measure self-concept as the subject's overall score on the Tennessee self-concept scale. So often operational definitions refer to the specific questionnaire or measuring device that is being used to measure that variable. I might measure performance, which is obviously a really vague variable unless I operationally define it. Here, I might define it as the number of goals scored out of 20 attempted penalty kicks. Different types of variables could include independent or dependent variables. This may be review to most of you. The independent variable you can think of as being like the cause variable. Again, we might not be able to establish a cause and effect relationship if we're not doing experimental research, but you can think of this as the one that you're proposing to be the one that actually acts on the dependent variable. So it's sort of being posed as the cause. It may be controlled by the researcher to test its effect on the dependent variable. Again, if you're doing an experimental study, some examples of independent variables would be an intervention, some drug treatment, some school curriculum, some training program, or something like that you want to see if it works or not. A dependent variable would be the effect variable, and this is measured in response to the independent variable. Some examples would be some outcomes like running speed, mental health outcomes, exam scores, etc., etc. So let's apply the terms. Go ahead and pause the video and answer the questions on your own, and then I will give the answers. So in number 1, the constants are the course. So Research 610 is constant for all the students that are taking the exam. We assume the exam itself is a constant. I'm not giving different exams to different students. I'm giving them all the same exam. Maybe we can assume that they're all taking it in the same room at the same time of day and things like that. Those will be constants. Number 2, I could operationally define their exam score as the percentage of questions that they get correct out of the total number of questions. I could operationally define the amount of time taken as the number of minutes that pass between me handing the test out and them handing each student handing the test in. The independent variable would be the time taken to complete the exam. The dependent variable would be the exam score. Again, I'm not necessarily going to be able to establish a cause and effect relationship here because it's just a correlational study, but I can still have, I guess, sort of a notion that the time taken on the exam might influence how they do on the exam. It might actually be the reverse, though, in terms of causation. So you could probably make an argument in the reverse as well. So I also wanted to go over the distinction of data as either categorical or continuous. So here are some examples of closed-ended survey questions. All right, so please circle the college sport you play, either tennis or volleyball. We're assuming that I only have athletes of tennis teams or volleyball teams in my study, right? How many years have you played the sport? So choose one of the options. Rate your ability to return serves in your sport. 1 poor, 2 below average, 3 average, 4 above average, 5 excellent. And how many years have you played the sport? And just indicate the number of years. So it's kind of like the question in green, except I'm not giving categories. In this case, I'm just asking the person to report how many years. And finally, what is your height in inches? And so here are some examples of data that I may have collected from 4 people using the questions on the previous screen. So I have 2 tennis players, 2 volleyball players, and you can see how they responded in terms of the years they've been playing, their ability to return serves, the years just reported as a number of years, and their height in inches. So going from left to right, it's going from categorical data where I have categories of sport and years but placed into categories to continuous where I have all sort of range of numerical information. So whether data are categorical or continuous is also related to something known as the level of measurement of the data. So levels of measurement are determined by specifically how it's measured and recorded. For example, I might look at handedness as either left-handed or right-handed. I might look at height as being measured in inches or centimeters. I might ask people, similar to in the previous examples, I might ask it as categories, or I might just ask them in years, what is your age? And each of the different ways of asking these questions, and also, you can think back to some of the examples in the previous slides, the different ways that those questions were recorded will influence the level of measurement, which then influences the statistical methods that we can use to analyze those data. So I'm going to go through each of the different types of levels of measurement, and those are called nominal, ordinal, interval, and ratio. So nominal data refers to names, labels, categories. So basically, like purely categorical information, for example, gender, city of residence, eye color, study group, whether it's the control group or the treatment group, where there's just no numerical quantity implied by the data. So these are nominal data. Ordinal data gives an indication of the rank or order of data, but we can't really quantify the differences between them. So for example, I might ask someone, how do you feel? And give them the choices to report either bad, okay, good, or great. Even if I put those on a Likert scale where it's like 1 for bad, 2 for okay, 3 for neutral, 4 for great, I don't know specifically what is the numerical difference between bad and okay, or the difference between good and great, etc. And it's a similar idea for other Likert scale questions like, do you strongly agree, agree? Are you neutral? Do you disagree, strongly disagree? Or what income bracket are you in? Are you in the lowest 20%? Are you in the highest 20%? Or one of the ones in between? So again, I might get a sense of rank or order from these data, but I don't know how to quantify the differences between them. With interval data, there are meaningful distances and differences between the values, but there's no meaningful zero. And the consequence of this is that I can make comparisons by adding and subtracting, but it doesn't make any sense to make comparisons by multiplying and dividing. And I'll give some examples to show what I mean by that. But just some examples of interval data would be temperature on a Fahrenheit or Celsius scale, because you don't actually have an absolute zero on those scales. You can have negative temperatures in Fahrenheit and Celsius. And another example would be certain standardized test scores like the GRE or the SAT. I'm not sure if this is currently the scale that they use, but at one point the scale was ranging from 130 to 170, so there's no meaningful zero. Therefore, I can basically say like so-and-so did 20 points better than someone else, but I can't really refer to it in terms of ratios like percentages or fractions to compare people who got different scores. Maybe this will become clear when I talk about ratio on the next slide. I know it's a little bit confusing at this point, like what is meant by, making these comparisons by ratios, like multiplying and dividing. Well, with ratio data, you can do exactly that, because you have data that are numeric and have meaningful distances between them, and also have a meaningful zero to their scale. So for example, you can figure out someone's salary in terms of dollars. You can ask people how many children they have from 0 on up to whatever. You can ask people their height in centimeters, their weight in kilograms, their heart rate in beats per minute. The units of measure don't matter so much as, is there a meaningful zero? So, for example, I can have 0 children. I can have 2 children, and I have half as many children as someone who has 4 children. So that's the type of comparison I mean when I'm talking about multiplying and dividing. It does make sense to multiply and divide because 0 children makes sense. A lot of students will ask, well, what about like heart rate? Like 0 beats per minute doesn't make sense. Somebody would be dead if their heart rate was 0, or their height being 0 centimeters. That doesn't make any sense. And that's true, but there is some meaning to those values. And what I would think more about is not whether there's meaningful 0, but if you make a comparison, can you use multiplication and division? So for example, if you have someone who's 180 centimeters tall, they would be twice as tall as someone who's 90 centimeters tall. If someone's heart is beating at 120 beats per minute, their heart is beating twice as fast as someone whose heart is beating at 60 beats per minute. So you can make those ratio comparisons with ratio data. You cannot make such a comparison with interval data. Like I was talking about earlier, it doesn't make sense to compare temperatures and say, 60 degrees is twice as hot as 30 degrees, because again, you have this possibility for negative values to those scales as well. So just to summarize the levels of measurement, so nominal data is most like categorical data, ratio data is most like continuous data, and that's kind of a continuum varying from categorical to continuous. So all of these types of data are mutually exclusive and exhaustive. Those are fundamental characteristics of all variables. Ordinal, interval, and ratio have order to their scale, whereas, as I said before, nominal has no numerical quantity to it at all. Interval and ratio data have meaningful distances between them, whereas ordinal does not. And only ratio has a meaningful 0 that allows those ratio comparisons using multiplication and division. And that is all for our coverage of the types of variables. I'll see you soon. Thank you.